So our lesson today is the first lesson of chapter 9, and this is our last chapter. So all of chapter 9 is about exponential functions and logarithms. So today's kind of just the introduction to what an exponential function is and how to graph them. And then over the next few days, we'll get into logarithms. So as I was preparing for this lesson, I learned something that made me really happy. So you know how like groups of animals are called like different things, you know, so like you have like a herd of cows, but then there's like more unique ones like a murder of crows, or there's also, what was the one for hippos? I think it's like a bloat of hippos or something like that. So I was making a word problem to kind of start introducing the idea of exponential functions. And I found out that a group of rabbits is called a fluffle, which made me so happy. So I just had to tell you guys because I thought it was funny. So let's say that you have a fluffle of 6 rabbits, and every month your fluffle doubles because rabbits reproduce really quickly. I don't know if they reproduce that quickly, but we're just going to say that they do. And if we wanted to describe how many rabbits we would have after X number of months, that would be an exponential function. So let's just look at this for a couple different values of X. So if X is 0, so like after 0 months, that's just when we're starting. So we would have 6 rabbits after 0 months. And how many rabbits would we have after 1 month? 12, right? Because it doubles. Then after 2 months, how many would we have? 24. And how many would we have after 3 months? 48. Yep. Because if you double 24, that becomes 48. So what we want to look at is how many rabbits will we have after X number of months. So instead of having a specific value like 1, 2, or 3, we want to look at how many rabbits will we have after X number of months. So as we look at these numbers, we know that the pattern is that we're multiplying by 2. So that's the pattern. But how could we write an equation that would tell us the number of rabbits we have after X months? Might help if we write down how we calculated it. So how did we figure out that after 1 month, we have 12 rabbits? Like, how did you get the number 12? 6 times 2, okay. And then how did we get the number 24? Yeah, yep, so we did 12 times 2, but we could also write this as 6 times 2 times 2, right? Because the way that we got the 12 was by doing 6 times 2. And that would mean that for the 48, we doubled this number. So this would be 6 times 2 times 2 times 2. And our original amount is just 6. So when we write it out like that, does that help us find a pattern that we could use to write an equation for the number of rabbits after X months? Yeah. So the equation will exponent? Yes. Yep, exactly. So this expression will tell us how many rabbits we have after X months. And we could write this in function notation by saying the number of rabbits, let's do R instead of F since we're talking about rabbits. So the number of rabbits after X months would equal 6 times 2 to the X power. So an exponential function is basically one where you have an exponent in your, a variable in your exponent. And you may have stuff being added or multiplied in the exponent as well. You might have something added or multiplied here or added to the end. So you can adjust exponential functions just like how we adjusted quadratic functions. But the basic idea is that an exponential function will have the variable in the exponent. So this is different than a polynomial because a polynomial, you have the exponent raised to a power like x squared or x cubed or something like that. But an exponential function has the variable in the exponent. So on your homework, a large majority of your questions will be graphing exponential functions. So we'll talk about that in just a second. But if we go back to our rabbit example, exponential functions, when they're multiplied by something, this is going to be your initial amount. So like in our situation with our fluffle of rabbits, we started off with 6 rabbits. And so that's this number. And then this number tells us what we're multiplying by each month. So since we were doubling it, this is a 2. But if we look at this equation, what this is telling us is that our original amount is 3, and it's quadrupling every time X increases. So if X was talking about months again, it would basically say that we're quadrupling it every month. Everybody good with kind of the structure of that? Okay, so when we graph these, basically you're just graphing solutions to the equation. So the way that you would do this is you would just think of some numbers that are easy to plug in for X. So I might say, okay, well, if X is 0, then in order for my equation to be true, Y would have to be 3 times 4 raised to the 0 power. And order of operation says you do exponents before multiplication. So you'd say 4 to the 0 is 1. 1 times 3 is 3, which makes sense because if X is 0, that's just going to give you your starting amount that you start with. Then you could also say, well, if X is 1, then Y is going to be 3 times 4 to the first power. 4 to the first is 12, or sorry, 4 to the first is 4 times 3 is 12. And you could also plug in a 2, you know, and you get 3 times 4 squared. I don't know what 3 times 16 is. Well, no, maybe, is it like 48? Okay, so you get 48 if you plug in a 2. And already that solution is way off of the graph. Because what we've found so far is that when X is 0, Y equals 3. When X is 1, Y equals 12, which is up here. And if X equals 2, then it's going to be like way up there at 48. So exponential functions grow pretty quickly, even if this number is relatively small. And then if we go in the other direction, see what the graph looks like on that side. If I plug in a -1, I have 3 times 4 to the -1. And remember, negative exponents create reciprocals. So 4 to the -1 is going to be the reciprocal of 4 to the first power, which is 1/4. So this would give us 3/4. And we can see on the graph that this point is about where Y equals 3/4. Then if I were to plug in a -2, 3 times 4 to the -2 is going to be 3 times 1/16, which is 3/16. Because 4 squared is 16. And so 4 to the -2 is the reciprocal of that, which is 1/16. Is everybody good with that on how those fractions are found? And basically, when you're graphing these, this will never go below, like it's going to get closer and closer to 0, but you'll never get a negative output. Because regardless of what negative exponent you put in and how tiny your reciprocal ends up being, this number will still be a positive number. And so you basically have an asymptote here at 0 where it gets closer and closer and closer to 0, but it doesn't ever actually cross 0, if that makes sense. So exponential functions will always follow some type of shape like this. Depending on like if you have numbers subtracted or multiplied by a negative or something, it might be flipped upside down or reflected or moved side to side. But the basic structure will always look something like this. And that's just a feature of exponential functions. All right, so let's do a quick check-in. Scale of 1 to 5. How are you guys feeling about graphing exponential functions? Okay, cool. So on your homework, you don't have to plug in like 5 numbers like I did. On your homework, I believe, let me go to one of the questions. They have this function tool where you only have to graph 2 points. So basically you just choose whatever 2 numbers you think would be easy to plug in. So for example, on question 6, I have the equation Y equals 1/3 to the X power. That's the function I'm trying to graph, or the equation I'm trying to graph. And so I only need to graph 2 of them if, like, when I'm actually doing the homework, because that's what the function or the tool requires. But I'm going to graph a couple more since I'm graphing this by hand. So what do you guys think would be some easy numbers that you could plug in for X? Yeah, -1. Okay, awesome. Yeah, that would be good because if I do 1/3 to the -1, 1/3 to the positive one is 1/3. And so to the negative one is the reciprocal of 1/3, which would be +3. Yeah. What? Sorry, say that. Oh, okay. Sorry, I heard you wrong. We'll do 0 as well. Okay, -1 would be a good one though, because since they gave us a fraction, a negative exponent will create the reciprocal of that, which makes it a whole number. Versus if you were to plug in a positive one, you would get 1/3, which is still a solution, but it's not an easy one to graph. So let's go with 0 since that's what you actually said. And if we plug in a 0, what is the output? Yep, 1, because anything to the 0 power is always 1. And this actually gives us enough points to see kind of what the graph is going to look like, because I have 0, 1, and then I have -1, 3, and then I have 1, 1/3. And if I wanted to, I could also maybe plug in a -2, because if I do 1/3 to the -2 power, 1/3 squared is 1/9. So 1/3 to the -2 power will be the reciprocal of 1/9, which is +9. And that would give me this point here. And so I can see that my function graph is going to look kind of like this. And that's what my exponential function will look like. But again, on your homework, you don't have to do this many points. You just have to choose 2, and then the tool will graph the rest of them. All right. Any questions on how to graph it, especially if they have fractions in it like that? Okay, cool. So you have a whole bunch of graphing ones, like on question 8. On this one, you have a graph where you have a -x in your exponent. So in this case, you may want to, like, you just think about what's going to be easy to plug in. So I would say, well, if I'm trying to do y equals 2 to the -x, I might plug in a -1, because 2 to the -1 is going to be 2 to the +1, which is an easy number to graph. So you just kind of choose your x values based on what you think would be easy to plug in. You might also get some like this, where you have some addition or multiplication inside of the exponent. And on question 9, you'll be asked, I think everybody has the same question on this one actually, but you'll be asked to graph y equals e to the x. And this e is an irrational number called Euler's number. And this is like it's just a number kind of like pi is. So you know how pi is 3.14159 is this decimal that goes on forever. Euler's number is the same thing, and it's represented with the letter E. So if you forget what this is, you can always Google it, just like type in number E, and it will say what it is. But this number shows up a lot in exponential functions because you can use it to model things like compound interest, because compound interest is repeatedly multiplying by the same interest rate. And so it's kind of like an exponential relationship. It also shows up in like population modeling, like how fast a population is growing. So there's a lot of applications for this number, but you will see it on a couple questions on your homework. So like on question 9, when they ask us to graph y equals e to the x, just know that e is a number. It's not a variable, it's a specific number that's 2.71 whatever. So I think it would be easy to have x equals 0, because if I have this number 2.71 whatever raised to the 0 power, that's just going to be a 1. And then I also think it'd be easy to have x equal 1, because if I have 2.7, et cetera, raised to the first power, then my output will be the number e, 2.71, et cetera. And you can, I think that should be enough points to figure out what this graph would be, because 0, 1 is this point. So that doesn't really help us eliminate an option, but this one does, because if I go to where x equals 1, on the first graph, my output is a 4. So it's definitely not that one. Then on this one, if I go where x equals 1, this one is a decimal that's between 0 and 1. So it's not that either. But if I go to this one and I go to x equals 1, you can see that the graph goes through about 2.7. And so that would be our graph for this equation. Any questions on that? Okay. The other place Euler's number will show up is on question 14. So on question 14, you're told that the cost of a can of Coca-Cola in 1960 was 10 cents. The exponential function that models the cost of a Coca-Cola by year is given below, and the equation they give us is C of t equals 0.10 times e raised to the 0.0576 t, where t is the number of years since 1960. So notice what t is representing here. So t is not the year number, it's the number of years after 1960. So when they ask you to find the expected cost of Coca-Cola in 1985, well, 1985 is 25 years after 1960. And so in this case, t would equal 25. And then you're asked to find the cost. So basically you just plug it in and calculate it. So you would say the cost in 1985 is going to be 10 cents times e raised to the 0.0576 times 25. And to simplify this, you would multiply these two numbers together, which would give you some decimal. Could someone actually calculate that for me and tell me what that is? $1.44. Okay, awesome. So my exponent simplifies to 1.44. And then order of operations says I need to do my exponent before I multiply by the 0.10. And on many calculators, there will actually be an E button where like you'll be able to do E raised to something. So you'll have to look at your calculator and see if yours has it. But even if it doesn't, you can use this number for E and it will give you a pretty good approximation. Because technically the decimal does go on longer, but this decimal is close enough and it will give you a close enough approximation. So you would take this number, or if your calculator has an E button, you can just use that. And you would raise it to this exponent and then you would multiply by 0.10. And that's how you would do question 14. And there's other spots as well, like you say, oh, like 1990 is 30 years after 1960. And 2015 is 55 years after 1960. And so you plug it in a couple times with different values for t. So that's question 14. I think we went through almost everything. Oh, there's one other type of question that will show up, and this is at the very beginning. And it's not terribly different from what we've been doing. But on these ones, they're just asking you to evaluate the functions. So like on number 4, they're asking you to find the output of g when you input a -4. So you'd say, well, g of x equals 1/3 raised to the x. So g of -4 is going to be 1/3 raised to the -4, which is going to be the reciprocal of 1/3 raised to the 4th. So this is going to equal 3 to the 4th. And I think that's 81. And so that would be what this one would be. And so on question 1, you'll basically just go through and evaluate all of these things. And on some of them, you may have 2 evaluations that are added together or subtracted. So like in this case, you would input a 2 into F, input a -2 into G, and then add the results together. Question 2 is similar because question 2 asks you to evaluate this expression. So this expression is saying you input a -2 into G, figure out what that gives you, input a 1 into G, and then subtract those 2 results, and then divide by -2 minus 1. So I'll go ahead and do this one as an example. So G of X is 1/2 raised to the X. So G of -2 is going to be 1/2 raised to the -2. Then we'll subtract G of 1, which is 1/2 raised to the 1 power, all over -2 minus 1. So 1/2 to the -2, the negative creates a reciprocal. So the reciprocal of 1/2 is 2, and 2 squared is 4. So we'll get 4 minus 1/2 to the 1, which 1/2 to the first power is just 1/2. And this is all over -2 minus 1, which is -3. Then you just go through and simplify this and you say, well, 4 minus 1/2, in order to simplify that, I need to have common denominators. So I would write 4 as 8/2, because that's what the number 4 is if you make it have a common denominator of 2. And then that would equal 7/2 divided by -3. And whenever you do a fraction divided by a number, you can think about it as multiplying by the reciprocal. So you could think about this as 7/2 times -1/3, which would be -7/3, or sorry, -7/6. Like that. So most of the hard work is just simplifying it. But the basic idea is you just plug in these numbers into the function. I think on question 3, there's also one where you're not plugging in a number. So in this case, you're doing f of x minus f of 3 over x minus 3. So when you plug in x into the function, you get 3 to the x. Then when you plug in a 3 into the function, you get 3 cubed. And this is all over x minus 3. 3 cubed can be simplified, but nothing else can because we don't know what x is. So the most simplified version of this expression would just be this, because we don't know what x is, so we can't combine anything else. So I think that's everything you guys need to know for your homework. Do you guys have any questions on it? Okay, awesome. Now I'll let you guys go ahead and get started on your homework. I'm available to answer any questions on this assignment, as well as any of the questions over the last few assignments if you're finishing up some late assignments. So let me know if you have any questions. Also, if you didn't sign the attendance sheet yet, does anybody know where it's at? Who has the attendance sheet? You do? Okay. Did anybody not sign it? Okay, I'll go grab it.